Measurement uncertainty. Introduction. The automation measurements are taken so that useful data for the decisions process may be required. For result to be useful, it is necessary that their measurement errors be small in comparison to change, effects, or control process. Under evaluation, measurement error is unknown, but its limit may be estimated with statistical confidence. And this estimate of error is called measurement uncertainty. Error is defined as the difference between the measurement value and the true value of measurement. Uh, is as shown in Figure 5.1 is equal to measurement minus true, where e is equal to the measurement error measured is equal to the value obtained by a measurement through the true value of measurement. It is only possible to estimate with some confidence that the expected limits of error. The first major type of error with limits needing estimation is random error. The axioms or limits of a random error source are usually estimated with the standard standard deviation of the average, which is written as a guide to the automation body of knowledge, third edition, where the standard deviation of the average, the sample standard deviation of the data divided by square root of m. The number of values arranged for a measurement, the sample standard deviation, the sample average. Note is equation 5.2, and that n does not necessarily equal m. It is possible to obtain Sx for historical data with many degrees of freedom and to one greater than 29, and to run the test only m times. The test result is or average would therefore be based on m measurements, and the standard deviation of the average would still be calculated with equation f 5.2. Measurement uncertainty accuracy. Our needs are an estimate of the uncertainty of test results to make informed decisions. Ideally, the uncertainty of a well-run experiment will be much less than the change or test result expected. In this way, it will be known with high confidence, and the change or result observed is real or acceptable and not a result of errors from the test or measurement process. The limits of those errors are estimated with certainty. Are those errors source and their limits estimated. The uncertainties may be grouped into classifications to make them easier to understand. Classifying errors and uncertainty sources, there are two classification system in use. The final uncertainty calculated at a user confidence is identical for the two systems, no matter that classification system is used. The two classifications utilized are the International Organization of Standardization classifications and the American Society of Mechanical engineering classifications. The former groups errors and their uncertainties by type, depending on whether or not there is data available to calculate the sample standard deviation for a particular errors and its certainty. The latter classification groups errors and their uncertainties by their effect on the experiment or test. that is the engineering classification group errors and uncertainties by random and systematic effects with subscripts used to denote whether there are data to calculated that calculate a standard deviation or not for a particular error or uncertainty source. ISO classification. In the ISO system, errors and uncertainties are classified as type A if there are data available to calculate a sample standard deviation, and type B is if there are not to. In the latter case, the sample standard deviation might be obtained, for example, from engineering estimate, experience, or manufacturer's specification. The impact of multiple sources of error is estimated by root sum squaring their corresponding elemental uncertainties. The operating equation are as follows. Process transmitters. Introduction. With the emphasis on improved control and control quality, and with advanced control system, the significance and importance of measurement is often overlooked. In early industrial facilities, it was soon realized that many variables need to be measured. The first measuring devices consisted of a simple pointer display located in the processing area, a pressure gauge, for example, when the observation of a variable needed to be removed from the actual point of measurement. Hydraulic impulse line were filled with a fluid and connected to a readout device mounted to a panel for logical indications of a measured value. The need of transmitting measurement signals through greater distance become apparent as the size and complexity of process units increased, and control moved from the process area to a centrally located control room. Transmitters were enveloped to isolate the process area and material from the control room. In general terms, the transmitter is a device that is connected to the process and generates a transmitted signal proportional to the measured value. The output signal is generally 3 to 15 psi for pneumatic transmitters, and 4 to 20 MA for logic electronic transmitters. It has taken many years of these standards values to be adopted. Other scaled output values may be used and converted to these standard units. The inputs to transmitters will represent the value of the process to be measured and can be nearly any range of values. Example can be 0 to 1 psi, 0 to 100 psi, 0 to 100 in the in of water, 50 to 50 degree Fahrenheit, and 100 10 to 100 in in of level measurement, or 0 to 100 kPa mmHg, minus 4 to 120 degree centigrade, and 5 to 50 centimeter of level measurement. And the actual value of input measurement determine the process requirement. It is established during initial step and calibration of the device. Although transmitters have been referred to as transducers, this term does not define the entire function of transmitters, which usually has an input and output. The transducer is a device that converts one form of energy into another form of energy that is generally more useful for a particular application. I hope you like this video and don't forget to subscribe my YouTube channel. Thank you.